Swayam Prabha. Digital India. Educated India.
Welcome back to the manufacturing automation course. So far we have discussed what is manufacturing automation, how it can be defined. A truly automated system should actually have the ability to make a decision, carry out the decision, and to check whether the decision that they have taken is being performed properly or not. We have also seen the type on the what is the benefit. There is a lot of benefits for the automation. Then we have discussed that why we need the automation, reasons for automation and so on. So, next let us discuss some of the automation strategies which should be taken up, so that the productivity production rate can be enhanced in the manufacturing processes. So, first point is the specialization of operation, that is, we are saying that the use of special purpose equipment which will be able to perform one job precisely, okay, and that machine will be specially used for that particular operation. So, therefore, we are calling as that machine is a specialized machine for a specialization of operation. Second point is the combined operations. Combined operations do mean that this will reduce the number of workstations. So, the complex parts may need a large number of processing or a large number of assembly if the assembly is very complicated, and in case we can do the processing in different processing in one machine, in that case we can use minimum number of machines, and that will reduce the number of workstations. That is the strategy which we are calling as a combined operation. That means, few operations will be combined in one workstation or in a one machine, which will reduce the number of machines then. Next point is the simultaneous operations, and the simultaneous operations means that operations which are combined in a machine can be done simultaneously. Give you an example. For example, let us say combined operation. Suppose we need to turn a part, after that we need to chamfer it, after that we need to cut it in pieces. Okay. So, in one machine we can do that in a sequence. First you are turning, then another tool is coming for chamfering, then another tool is coming for parting the workpiece, parting tool. Now, the third point, which is the simultaneous operation, is that in one machine we are simultaneously doing these three operations. That means, we are reducing drastically the total processing time, whereas in case of combined operations, since we are doing many operations together in one machine, we are actually reducing the number of workstations, and in the third point we are simultaneously doing that, so that the total processing time is reduced. So, the productive capacity or the production rate will be increased, because production rate, as we know, that this is 1 upon the time, okay. Less time is more production rate. Fourth point is the integration of operations. That means, several machines which are linked together, okay, so that the parts could be routed from one machine to another machine. Next point is the increased flexibility. Increased flexibility is that the equipment that we are using can be maximally utilized, meaning that one machine can be used for producing different types of parts. Okay. As you understand that we are giving the example of numerically controlled machines, for example. Let us say if you take a turning machine, we call it a turning because only the turning operation can be performed. We cannot do the milling process, for example. All right. Whereas, if you take an NC machine, for example, NC machine with using the NC or the CNC machines, we can use many such operations together in one machine. So, we are using the flexibility, that means, we are using the machine utilization, we are increasing the machine utilization. Next point is the improved material handling and storage, that will reduce the non-productive time, okay. Meaning that in the normal production where we do not have the material handling and storage system properly, in that case the crane or a human being is taking the part and carrying from one machine to another machine, one workstation to another workstation, and they are being stored somewhere for which we have to find out where it is being stored. Whereas, in the case of automation, what we are calling is there is a concept of computer aided process planning, CAPP for example. There within in the computer program we can find out that where exactly that part is located. So, the automatic guided vehicle will be given that signal and it will go exactly to that particular position and take out the part. It will not take much time. And as you understand that if the assembly process or the manufacturing process for complicated parts, in that case the number of parts and the number of processes will be huge, a very large number. So, if you have to find out each part where it is located without any process planning, it will take a lot of time. So, overall the improved material handling storage as well will increase the production capacity, production rate. Next point is the online inspection. Online inspection is the correction of processes. I told earlier also that, for example, an adaptive control system can be used. So, during the process which can be inbuilt in the machine, so that during the process what kind of errors are being produced, and those errors will be rectified, and these first of all identified and rectified by the adaptive control system inside the machine itself. So, this is the online inspection. Or in the line, for example, flow line where we have the different machines which are linked together, in between there could be an inspection machine which will inspect each part which is being produced and give the signal that this is the error which is coming and this has to be rectified. Next point is the process control and optimization, that is to operate the individual process and the equipment more efficiently. Okay. So, here also again the process control will be that there will be sensors, sensors will identify the process performance and it will dictate the process how to make it in an optimum condition. This process control and optimization means that. Now, we are further extending the process control and optimization to the plant level, and this is the plant operation control. And the plant operation control actually this is for the overall the plant level. So, that means this concept of this process control is extended to the plant level, okay, to the factory level. And basically the finally the computer integrated manufacturing, this is the integration of the factory operations with the manufacturing processes, with the design, with the advertisement, with all the activities and the other business activities in the plant, they are all integrated using the computer network system. Next, let us see what are the types of automation that we have. Normally, we have three types of automations, that means fixed automation, programmable automation and the flexible automation. Let us see the fixed automation which is normally used in the mass production. Here the sequence of processing or assembly operations is fixed by the equipment configuration. Okay. What does it mean? Let us take an example of a standalone turning lathe, okay, and that lathe is the for a specialized operation. That means that lathe machine is designed for making a particular part. Okay. So, depending on the part configuration, depending on the part size, okay, we have to make relative motion between the tool and the workpiece. For that, suppose there are camshafts, okay, and those cams, the configuration of the cam is according to the configuration of the part, so that that part can be manufactured. Now, if we have to make another part, for example, of another configuration, then that machine cannot be used because that machine has a particular camshaft for producing that particular part. So, therefore, what we see is here the relatively inflexible, this fixed automation, the machines which are used in the fixed automation, or overall the fixed automation has relatively less flexibility, okay, in accommodating product changes, because here the high initial investment for the custom engineered equipment. I gave you an example of a lathe machine where a particular part is being manufactured. So, that machine is called the custom engineered equipment, because that equipment is made according to the customer's part, customer's order. Okay. So, if another customer is giving another order of different configuration part, that part cannot be produced by the machine, earlier machine, which was that is why we are calling it as a custom engineered machine or equipment. So, the first criteria for this fixed automation is the high initial investment for the custom engineered equipment. Next point, which should be highlighted for the fixed automation, is the very high production rate. And the high production rate, because that machine is a specialized machine which can be operated only for producing that particular part or those particular parts, okay. And that machine is doing it with a very high precision, very high efficiency. So, therefore, the production rate becomes very high, but as I said that here these machines are relatively inflexible. Let us take example of mechanized assembly lines which were invented in way back in 1913, or the machining transfer lines which were invented in 1924. So, these are the examples of the fixed automation, and this fixed automation is used, as I said, I am repeating that this is in the mass production basically. Next is the programmable automation, and you must have heard about programmable automation in terms of numerically controlled machines, computer numerical controlled machines, CNC, NC machines. So, the production equipment is designed with the capability to change the sequence of operations to accommodate different product configurations. So, the basic difference between the programmable automation and the fixed automation is that we are trying to increase the flexibility. Why it is required? Because our demand has changed. For example, today you are wearing a particular shirt, tomorrow you would not like to do that, because in the market you have different other design of the shirts, although your shirt is not old. Okay. So, making different shirts need different kind of skill or different kind of machine sometimes. Okay. So, a machine should have the flexibility, so that different configuration of the parts can be manufactured. So, this is one of the aspects of the programmable automation, where flexibility is increased overall. So, the criteria for the programmable automation is that high investment in general purpose equipment. You see the difference here, that earlier it was the custom engineered equipment for the fixed automation, where these machines were capable of making a particular part, parts of particular shape, size, finish, accuracy. Here what we are using in the programmable automation is the general purpose equipment, because these equipment will be able to manufacture different configuration parts of different configuration, and therefore, the investment will be higher. Okay. Second point is the low production rate with respect to fixed automation. Low production rate, because when you are changing the configuration from one batch of products to another batch of products, it needs some change in the machine. For example, in case of numerically controlled machines, you need to change the program, you need to change the pallet fixtures, for example. So, that will actually take time, so therefore, the production rate will be lower. And the third very important point is that flexibility to deal with the change in the product configuration. In one NC machine, you can actually produce a shaft, for example, then you can cut the gears, for example. You can also, there are machines which are capable of making the drilling, for example, and so on. So, in one machine your flexibility is very high and it is being utilized quite properly. And the examples, as I said, these are the NC machine tools, which have been the concept has come way back in 1952 in the Massachusetts Institute of Technology, and the industrial robots way back in 1961, okay, and the NC machine tool around 1952. Next is the flexible automation. Flexible automation actually one step ahead of the programmable automation. In case of programmable automation, what we are doing is that we are changing the program, okay, and we are changing the fixtures from one part to another part of one configuration to part of another configuration. So, that takes time. In case of flexible automation, that time is reduced to minimum. That change in the program is being done offline. When one part is being produced, the the program for the another part is being ready, it is prepared offline and then it is transmitted electronically, and the fixtures are also made on the pallet fixture, and as soon as one part manufacturing of one part is over, the pallet fixture comes in and the changeover in the fixture does not take time. So, here the high investment for a custom engineered system. So, therefore, the entire system is also will be custom engineered in the batch wise, and the continuous production of variable mixtures of products possible, and the flexibility is very high. It is even higher than the programmable automation that we have discussed. Example of the flexible automation is the flexible manufacturing system, which came way back in 1960. In the flexible manufacturing system, you understand that there are few NC machines linked together with the manipulators, with the robots, and there is a system control system consisting of the computer, which will control the NC machines, give the signal to the NC machines, program to the NC machine, and program to the robot for placing the part placing. This will be acting as a part placing mechanism. Next, let us discuss so called Detroit type automation, that is the automated flow lines. And here in fact, we will be discussing different aspects of the automated flow lines, as you can see here in the diagram. Now, the traditional symbol of the automation is the mechanized flow line. Okay. Now, this is the first example of the automated production to come, and the origin of the mechanized production lines or flow lines, these can be traced in the works of the Henry Ford, Chrysler in the city of USA Detroit city, and there the automobile industries of Ford, Chrysler, they are located. That is why this kind of techniques which is used in the automation, that is called the Detroit type automation. Now, here is an example of an automated flow line. So, you can see automated flow line will have the combination of different machines, and they are linked together by the material handling device. This is the material handling device. So, the material handling device is bringing the raw material from one part, one machine or one workplace to another workplace, and these are the machines which are stationary, and these machines can be either production machine, processing machine for example, or it can be assembly stations for example, where it is given ASBY in short, that is assembly, or it can be inspection stations, or it can be sortation stations and so on. So, basically they are actually linked together. Okay. That means, the parts are rotated from one workplace or one workstation to another workstation with the help of the material handling device, and the finished work part will be coming out of this. Okay. So, entire system is called the automated flow line, and the use of the automated flow line, the ultimate and the optimum use of the automated flow line was shown by Ford in his manufacturing and the assembly of automobiles in the city of Detroit, and finally, the result was the 10-second per car assembly. That was the history. Now, the objective of the use of the flow line automation, there are a few. First of all, to reduce the labor cost. Okay. And here it is very important to mention that the labor cost, particularly the loading and unloading, these are the very important factors which are being reduced or which are being eliminated overall. Second point is to increase the production rate. Of course, machines are linked together, the routing is less. Routing is, that means the from shifting the part from or the assembly from one machine to another machine, the time is less. So, therefore, the production rate will be increased. Third point is to reduce the work in process. That means, the work routing is so optimum that the workpiece, how much time the workpiece is located in the process will be less, duration of time will be less. Here also this will minimize the distances moved between the operations. Let me explain it to you. For example, if a part needs a turning, then milling, then drilling and so on. So, suppose if we put the turning machines together, drilling machines together, milling machines together, in that case first the turning will be done, then the milling, then the drilling and so on, and the part does not have to come back after turning to milling and then again turning and so on. So, overall it is minimizing the distance moved between the operations. Here also to achieve the integration of operations. So, all processes which are similar, they are integrated together. This is one of the advantages of the automated flow lines. Now, basically there are two general forms that the workflow can take place. Okay, as you can see in the diagram, the first is the inline type, that is called the inline type, and the inline type, in inline type all the machines are located in a line, in a straight line, more or less straight line. There are few rotations, okay, at a 90 degree, but overall all the machines are located, or machines are arranged more or less in a straight line. See here in this example, for example, this is the differential of an automobile, this is being machined. So, these machines are here, and the after machining up to that point, this is being turned, okay, at a 90 degree angle, and then again it is being machined in this. So, all the machines here, they are in a line, and in between we can have the inspection machines, we can have the heat treatment process, and then the final workpiece will be taken from somewhere here. Okay. So, this is the inline type, or we can have the rotary type. In case of rotary type, we have the stationary machines around a disc, or this is called the table or a dial. So, therefore, these machines are also called the dial indexing machines, dial indexing rotary machines. So, for example, here the raw part, raw material will be given here, and then it is being rotated to this workstation, and the machine is the part is being processed. After processing this, it will go to the next stop or the next workstation and so on, and it will come out, the finished workpiece will be coming out from here. Now, here you mind one thing, that this dial or the table, this is the indexing table, that means it will rotate and it will stop for some time, till the machine is being processed or the assembly is being completed. So, from here it will rotate up to this point and stop, and then again when the process is over in this station, it will go from here to here and so on. So, therefore, it is called the dial indexing. So, this is the indexing, and when it is stopping, this is called the dwelling. The time period during which it stops, it is called the dwell time, and the time period it is going from one place to another place, it is called the indexing time. Okay. And these concepts you must have heard in the Geneva mechanism, for example, because this kind of dial indexing machines, in many cases the Geneva mechanism is used, which is used for rotating and then, or indexing and then dwelling, and then again indexing and dwelling and so on. What is the what kind of choice you will be making, whether you will be taking the inline type or you will be taking the rotary type, that depends on whether your parts are smaller. For example, in case of rotary type, basically for smaller parts it is used, or if the assembly is small, okay, assembly small in the sense that assembly consists of, let us say, fewer parts, 10, 15 and so on. Or if the machines are smaller, normally in the rotary type the not very expensive machines are used. One very important point in the rotary type is that here we do not use the buffer stock or the buffer storage. Now, the concept of the buffer storage we will be discussing later in details. Let us come back to the inline type. For example, in the inline type, what happens is that if a machine stops, for example, if this machine stops, then next machine will not be getting the parts for assembly or processing, and therefore, in between these two machines we should have some buffer. So, if this machine stops, this machine can still take the part from the buffer and use it. So, the stopping of this machine will not affect the working of the next machine. That is the concept of the buffer stock. In case of rotary type, the buffer stock is normally not used, because these are the smaller machines and we expect these machines to be fewer breakdown. Okay. Whereas, in case of inline type, there has to be a buffer stock, because in the inline type we use the larger number of machines, and in rotary type the number of machines will be less. So, therefore, the buffer stock is not used in case of the rotary type. whereas it is used in the inline type. So, these are the criteria which you should keep in mind for selecting whether you will be going for the rotary type or you will be going for the inline type. These are some of the examples. For example, this is the rotary indexing machine. You can see the rotary indexing table here, and around that we have the machine. So, here we have the part. So, part will be indexed and it will stop for some time for processing or the assembly of the machine, and when the processing or assembly process will be done. So, the part will be transferred from one place to another place for the subsequent assembly, so or processing. So, this is an example of the rotary indexing machine, or for example, here. So, again here is the rotary table in the middle, and around that we have the machines for performing the operation. So, if we see this diagram, here this is the indexing machine where we have the workplaces, okay. These are the workplaces, and these are the stationary machines around the rotary indexing table, which is the rotary indexing table is rotating and indexing, or indexing and dwelling, rotating and stopping. Part transferred in the automated flow lines, how the parts are being transferred from one place to another place. There are various mechanisms, okay. Now, basically they are distinguished in the two motions, which is one is the linear motion, another is the circular motion. For example, if a part has to be transmitted from one place to another place and then it has to dwell. One example is this one. For example, see here we have the piston and the hydraulic cylinder or a pneumatic cylinder, and this is the slider which is connected to the hydraulic or pneumatic cylinder. So, it actually goes to and fro, all right, and while doing so, these are the links which are connected to the piston or the slider. So, these links will go in a circular way like that, okay. So, it is going towards the right or it is coming towards the left, it will do this kind of a motion. While doing so, there is a fixed rail and there is a transfer rail. So, on the fixed rail there will be the work carriers with the work parts, and then the transfer rail which is connected to these links, it will actually lift it, okay, lift the work carriers clear and then going to the next stop. So, it is like, if I have to show it, if you for example, this is the fixed rail. So, in the fixed rail we have the part, okay, we have the carrier, and here is the transmitting or the transfer rail is moving like this. So, while doing so, it is taking out the carrier from here, all right, and while going ahead, it is actually putting that on the other position. So, here you can see that the hydraulic cylinder is working and the piston is moving to and fro. This is doing the semicircular movement. While doing so, it is actually lifting the transfer rail, so that the work carriers are lifted up from the fixed rail and then transmitted to the next position, all right, from one place to another place. So, this is used in case when it is the sub assembly or the product will be transmitted from one place to another place. Other examples we will be discussing later. Thank you very much.